Hi everybody, welcome to lecture 19 of Electrical Engineering 331. In this lecture we will continue to talk about inverting Laplace transforms. One of the main forms that we have not considered yet is something that looks like this. X of s is equal to ds plus e over as squared plus bs plus c. Now, actually, if you look carefully, you'll see that in the last question on test 18, we actually did have one term that looked like this in the denominator of the Laplace transform we were considering, but we very quickly identified it as being a perfect square, and so that made the inversion of the Laplace transform very easy. But what we want to do in this lecture is to consider what happens when we don't immediately see what the factorization should be, and to see how to proceed in that case. And by the way, we're assuming here that a is not equal to 0, so that we know for sure that the degree of the denominator is equal to 2, and so the degree of the numerator then is equal to 1 if d is non-zero, is equal to 0 if d is equal to 0. But in either case, the degree of the numerator is less than the degree of the denominator, so we're ready to proceed with this problem. So one more time now, what we're assuming is that we don't see an easy factorization. Now of course, since this is a quadratic polynomial in the bottom, you can always use the quadratic formula to factor that. But I'm just going to show you another alternative. One of the things about the quadratic formula is that it can give you complex roots, and maybe you would prefer to avoid that. Now, admittedly, in the table there are entries that have complex poles, but I'm just going to show you another way to handle those problems. So anyway, the first thing that I would recommend doing if you have something like this is to go ahead and multiply the top and the bottom, the numerator and the denominator, by 1 over a. So you would get d over as plus e over a in the numerator, and s squared plus b over as plus c over a in the denominator. And the only reason for doing that is just to make the coefficient, the leading coefficient in the denominator, equal to 1. Now, at this point, we do a procedure that you might have seen before called completing the square. And the way that goes is the following. You know that, for instance, x plus y quantity squared is equal to x squared plus 2xy plus y squared. In other words, you might have heard it like this. If you have a binomial like x plus y, and you square it, you get the first term squared, multiply the first times the second, and double it, and then you get the last term squared. So we're thinking of these first two terms here in the denominator as being the first two terms that we would get from squaring some binomial. Now, what binomial would that be? Well, we have s plus, and now we have to pick something to add to the s such that when we square it, we will get s squared plus b over as. Well, remember that, as we just said, the middle term when we square this is going to be multiply the first term times the second term and double it. And so you see that when we do that, multiply this first term times the second term, we get b over 2a, and then when we double it, we get b over 2a times s, and then when we double it, we get b over a times s, which is exactly what we want. So that's how we have chosen this b over 2a, is we've chosen it so that when we square this, we're going to get b over as. We're going to get exactly this term. Now this may seem a little complicated at this point, but just bear with me, because once we're going to do lots of examples and you'll see that this is actually quite easy. Just think of it that we're going to take whatever this coefficient is and divide it by 2 to include it in this binomial that we square. Now, again, when we square this binomial, the first term we get out is s squared, and that's great because that matches this. The second term will be s times b over 2a doubled, so we get s times b over a, and that will match this. But we're going to get one more term out of here, which is b squared, or b over 2a quantity squared. And what I'll do is I'll subtract that b over 2a squared, because that is something extra that we don't exactly need. So the last term that is coming out, as we've already argued, the first term and the second term we do want, because they will give us a match with what's up here above. But that last term that comes out, when we square the b over 2a, we want to subtract that off. And then we bring down the c over a that we have there. Okay. And now the last thing we'll do before we begin to talk about how to analyze this, we bring down the numerator again, and then in the denominator, all I've done here is to write these two terms here, these constant terms in the denominator. I've written them in a different order, in the order c over a minus b over 2a quantity squared. Okay, well, that term, this constant term down here in the bottom, c over a minus b over 2a quantity squared, of course it can be, there's three cases here. It can be greater than 0, it could be equal to 0, or it could be less than 0. And we're going to see what to do in each of these cases. Okay, well, if c over a minus the quantity b over 2a squared is greater than or equal to 0, in either of those two cases, there is going to be a form in the table that has a denominator that looks like this. Now, for greater than, we get one form that matches that. Actually, we have two forms that match that. We'll talk about that. We'll look at an example. But there are two expressions in your table that will match it if this is greater than 0. And if it's equal to 0, there's 1. Or, I guess there's really a way you could consider it 2, but we're going to look at both cases, so don't worry. On the other hand, if c over a minus b over 2a quantity squared is less than 0, then that would imply that if we flip this, b over 2a quantity squared minus c over a must be greater than 0. Because it's just this same thing written in the reverse order. And if this is greater than 0, then it makes sense to talk about the square root of that. In other words, what I mean is the square root of that is a real number. So, in that case, we could write x of s in this way. The numerator is still the same, but now what I've done is to write this term right here. I have written it as this. And if you see how I have a square root squared, so if you just take away the square and take away the square root, then I have minus b over 2a squared and minus a minus, which is plus c over a. So that you can see it's exactly the same that we have up here. I've just written it in a different way. Now, why have I written the denominator in this way? Well, the reason is that if we look at this, the denominator is now written in the form of a difference of two squares. You see how this first expression is s plus b over 2a squared, and the second one is this square root squared. And you might remember from your algebra courses that the difference of two squares can be easily factored. X squared minus y squared is equal to x plus y times x minus y. So that means that this denominator can be factored into, okay, x is s plus b over 2a, and y is this square root. So we have s plus b over a plus the square root, and then s plus b over a minus the square root. That's x plus y, x minus y. And then we just bring down the numerator. Okay, well, now we can break this up into alpha over the first term plus beta over the second term. And remember now that b over 2a, all this stuff besides the s is just a constant. So we have s plus a constant there, s plus a constant there, and of course that matches a form that we have in the table. So what we conclude then is that whether c over a minus b over 2a squared is greater than 0, equal to 0, or less than 0, in any of those three cases, we have it covered. We can look at the table. We may have to do a little bit of work, but we will finally be able to look at the table and invert the Laplace transform x of s. So as I said, this probably looks a little bit complicated, but once we look at some examples, I think you'll conclude that it's really quite simple. So let's look first of all at this example 19.1. x1 of s is equal to minus s plus 5 over s squared plus 10s plus 21. And if you look at our basic model up here, you see that the coefficients from left to right in the denominator are a, b, c, and then in the numerator are d and e. So you can see then that a is 1, b is 10, c is 21. I've written them down below here to match the fact that they're in the denominator, and then up in the numerator, d is -1 and e is 5. So if we check that expression c over a minus b over 2a quantity squared, then in this case we would get 21 minus 10 over 2 quantity squared, or 21 minus 25, which is -4. So this is going to be the case where c over a minus b over 2a quantity squared is less than 0, which you might remember is the last case we looked at above. Now I want to stress, you shouldn't have to ever analyze this. You don't have to waste your time looking at a, b, c, d, and e and calculating c over a minus b over 2a squared. Don't do that. Just go ahead and proceed with the problem. But in the examples, in each example, I will call your attention to what is equal to, so that you can compare what we're doing in the examples to what we did in the theoretical discussion that we just concluded. But when you're actually solving one of these problems yourself, I don't recommend that you do that. I think that that's just really sort of a waste of time. Okay, so this form right here is not in the table, so that's good. We can go to the next thing. What about the degree of the numerator? Is it indeed less than the degree of the denominator? And the answer is yes, because the degree of the numerator is 1 and the degree of the denominator is 2, so that's good. And so now we want to break this up as much as we can and see what happens. So we have minus s plus 5 in the top, and then notice then that in the bottom now, remember how I told you to take this second coefficient, b, and divide it by 2. So I'll have s plus 5 squared. And notice that if we just look at this and squared it, it would give us s squared, which would match this term, s squared. Multiply the first times the second and double it, so 5s doubled is 10s, so that matches that. But then we would also get a plus 25 when we squared the 5. And we don't need that plus 25, so we're going to subtract 25. So we have minus 25 to make up for the fact that we have a plus 25 as the last term from squaring this binomial. We're going to subtract 25, and then we bring down this 21. Okay, and now we observe then that, of course, minus 25 plus 21 is minus 4. So there's that, that minus 4. So like I say, this is popping out when we do the procedure. There's no real need for you to calculate it up here. Okay, so we see, of course, 4 is 2 squared. And so we can write the Laplace transform like this, and then we immediately see that the denominator is the difference of 2 squares, where we can think of x as being s plus 5 and y is 2. So the denominator will factor is s plus 5 plus 2 times s plus 5 minus 2. That's x plus y times x minus y. And we just bring down the minus s plus 5 in the numerator. And of course, 5 plus 2 is 7, 5 minus 2 is 3, and so x1 of s can be written like this. Now, let me be perfectly clear on this. If you see up here, if you immediately see that s squared plus 10s plus 21 is equal to s plus 7 times s plus 3, then by all means go ahead and factor it, and that will save you a little bit of time. But what I'm showing you here is that you don't have to see it. And you also don't have to use the quadratic formula. If you will just use this technique of completing the square, this is always going to work out for you. So it's just something that is sort of nice because it works in every case. Okay, so however you arrive at the conclusion, though, we see that x1 of s is equal to minus s plus 5 over s plus 7 times s plus 3. So let's see. Oh, this is somehow, this has gotten sort of garbled here. Let me see if I can clean this up. Let's see. Oops, that's not what I wanted for sure. Okay. Okay, I'm going to have to clean that up. So let me stop the recording for a moment and clean that up. Okay, so now we have that those garbled letters straightened out. So again, we found out that x1 of s is equal to minus s plus 5 over s plus 7 times s plus 3. And so we write that as x1 of s is equal to theta over s plus 7 plus gamma over s plus 3. And yes, ordinarily I would say a over s plus 7 plus b over s plus 3, but I didn't want to cause any confusion with the a and b we have up here, and so that's why I chose to call it theta and gamma. But theta and gamma are just some constants that we're trying to find. Okay, we're using the Heaviside method then, and that's step 4, using the Heaviside method to to find the coefficients, and hopefully with the Heaviside method, and the Heaviside method will work here. So theta is equal to s plus 7 times x1 of s, evaluated at s equals negative 7. So when we multiply x1 of s by s plus 7, we just are left with minus s plus 5 over s plus 3, and when we evaluate that at s equals negative 7, we get negative 3. On the other hand, since gamma is over s plus 3, then the Heaviside method will say that gamma is equal to s plus 3 times x1 of s, evaluated at s equals -3. And so multiplying this by s plus 3, we get minus s plus 5 over s plus 7. Evaluate that at s equals -3, and we get 2. So gamma is equal to 2. So if theta is equal to -3 and gamma is equal to 2, then this expression becomes -3 over s plus 7 plus 2 over s plus 3. And of course, you can see this form. Both of these are a form that are that's in the table. And so we have x1 of t is -3e to the -7t plus 2e to the -3t u of t. So that turns out to be quite simple. Now let's look at another case. Here in 19.2, we have x2 of s is minus s minus 1 over s squared plus 4s plus 4. And again, if you wish, you can identify the values for a, b, c, d, and e. And if you do that, you will find that c over a minus b over 2a quantity squared in this case is equal to 0. And so again, that's a different case that we considered in our initial discussion. And so if you wish, you can look at that. But again, I don't really think there's any need to do that. Let's just proceed and see what happens. Okay, well, when we look at this, we don't at least immediately see that it's a form in the table. So I'll check that. And the degrees are okay. The degree of the numerator is strictly less than the degree of the denominator. So let's see what happens. Okay, here is x2 of s. And as usual, then we will attack the denominator by trying to complete the square. And remember, we'll have a binomial squared, and the second term of the binomial will be 1/2 of the coefficient of s. So since the coefficient is 4, we have 2 here, s plus 2 squared. And just to check, if we square this, we get s squared, which matches that. Then the first times the second double it will give us the 4s. But we'd also have a 4 popping out there. So we subtract off 4, but then we add in this 4. And so you see then that we end up with minus s minus 1 over s plus 2 squared, and then minus 4 plus 4 is 0. So here's that 0 that we're talking about. Okay, so minus s minus 1 over s plus 2 squared, we've seen something similar to that in lecture 18 and test 18, and we know that we need to expand it as theta over s plus 2 squared plus gamma over s plus 2. Remember that the number of unknown coefficients here will be equal to the degree of your denominator. Now, that's not to say that all of them will always be non-zero, but at least in your expansion, you should have the number of unknown coefficients should be equal to the degree of the denominator. Okay. Well, you might remember that when we have this repeated root case like we do right here, that the Heaviside formula for theta is just to multiply x2 of s by s plus 2 squared and then evaluate it at s equals -2. So when we multiply x2 of s, which is right here, when we multiply that by s plus 2 squared, we just get minus s minus 1, and then when the s plus 2 squared in the bottom will cancel when we multiply by s plus 2 squared in the top, so we're just left with 1. And when we evaluate minus s minus 1 over 1, when we evaluate that at s equals -2, we get a negative of a -2, which is 2, minus 1, which is 1. So theta is equal to 1. Now, in previous cases, when we've had problems like this, I have evaluated the second coefficient by just picking some value of s. I never have used the derivative formula that is given in the book. But in this case, it's convenient to use the derivative formula because we're just taking the derivative, in this case, of this very simple expression. So in this case, I'll use the derivative formula that the book has. So it says then that gamma is equal to the derivative with respect to s of this right here, s plus 2 squared times x of s, and then evaluate that derivative at s equals negative 2. Keep in mind now, when you do this, you take the derivative first and then evaluate at s equals negative 2. You don't evaluate at s equals negative 2 and then take the derivative. Okay. So when we multiply by s plus 2 squared, multiply x2 of s by s plus 2 squared, of course, as we set up here, we just get minus s minus 1 over 1, and the derivative of that with respect to s is just negative 1. And so, negative 1 is just a constant. It doesn't matter where we evaluate s. So, so the derivative is negative 1, and that means that gamma is negative 1. And therefore theta is 1, gamma is negative 1. We plug that in right here for x2 of s, and we end up with x2 of s is positive 1 over s plus 2 squared minus 1 over s plus 2. So x2 of t is t e to the minus 2t minus e to the minus 2t u of t. And that concludes that example. Okay, let's look at still another example. Let's suppose we had s plus 4 over s squared plus 8s plus 16. Again, if you want to, you can identify A, B, C, D, and E, and you'll see that this is another case where C over A minus B over 2A squared is 0. But something just a little bit different will happen this time. So let's see how it goes. The form, at least glancing at it without thinking about it too much, this form is not in the table. The degree of the numerator is indeed strictly less than the degree of the denominator, so we're okay, and we can proceed with the problem. Again, now you can probably look at this and see pretty quickly how to factor the denominator, and if you can, that's fine. But if you want to, you can always go with the completing the square method. So the binomial will be s plus, and then we take 1/2 of this coefficient, so that'll be 4. S plus 4 squared, and then since we have a 4 squared there, we want to subtract 4 squared, and then bring down this term, which is 16. And you can see then that what we end up with is s plus 4 over s plus 4 squared, which is just 1 over s plus 4. So this is another thing that can happen in the case where c over a minus b over 2a quantity squared is 0. And in this case, then x3 of s is 1 over s plus 4. We don't even have to use the Heaviside method because there are no remaining unknown coefficients. And of course, it is really easy to invert this, and we get x3 of t equals e to the minus 4t u of t. So, so we've looked at what happens in the case where c over a minus the quantity b over 2a squared is less than 0. And we've looked at what happens when it's equal to 0. Now let's look and see what happens when that quantity is greater than 0. And this is the, I guess in some ways you'd say this is the most complicated case. So let's watch this carefully to see what happens. So suppose we had x4 of s is equal to 2s minus 1 divided by s squared plus 8s plus 25. Now let me call to your attention the fact that if you use the quadratic formula to try to find the roots of this denominator polynomial, you would come up with complex conjugate roots, and that is correct. And we could tackle this problem in that way with complex conjugate roots. But I think that it's fair to say that when you do that, there's a higher probability of error. And so the completing the square method is particularly nice for this case, where c over a minus b over 2a quantity squared is greater than 0. So let's see how this will go. Okay, again, this form is not in the table, and the degree of the numerator is strictly less than the degree of the denominator. So let's see what we can do with this. x4 of s is 2s minus 1 over s squared plus 8s plus 25. And so we're going to use the completing the square method. And again, we take this coefficient of the second term and divide it by 2. So 8 divided by 2 is 4. So we're going to put s plus 4 squared. And the last term coming out of there will be 16. So we subtract off the 16. And then here we have 25. We'll bring that down. And you can multiply this out, and you'll see that if you multiply out and do all the operations here on the bottom, you will get s squared plus 8s plus 25. So we haven't changed anything. We've just written this in a more convenient form. Okay, minus 6 plus 25, of course, is 9. And 9 is the same thing as 3 squared. So we can write the bottom like this: s plus 4 quantity squared plus 3 squared. So now that we have this, we will, if we look at the table, we will see that there are two forms that match this s plus 4 squared plus 3 squared in the bottom. One is s plus 4 over s plus 4 squared plus 3 squared, and the other one is 3 over s plus 4 squared plus 3 squared. So we'll have theta as the coefficient of the first term and gamma as the coefficient of the second term. By the way, this, as we'll see, this is the Laplace transform of e to the minus 4t cosine 3t u of t, and this is the Laplace transform of e to the minus 4t sine 3t u of t. So that's that's where I'm getting these two forms. Okay, so now to find theta and gamma, I think the easiest way is just to note that the right-hand side, if we put it all over one denominator, it's equal to theta. We get theta times s plus 4 times theta plus 3 times gamma. And that's the numerator here. And of course, the numerator on the left-hand side is 2s minus 1. And so, and notice the denominators are the same. So we just have to compare the powers of s in the top to finish this problem. The only s term on the left is 2s. The only s term on the right is theta s, so immediately we conclude that theta is equal to 2. And then the constant term on the left is negative 1, and the constant term on the right is 4 theta plus 3 gamma. So 4 theta plus 3 gamma must be equal to negative 1. But we've already concluded that theta is equal to 2, so 4 theta is 4 times 2 or 8, so we have 8 plus 3 gamma is negative 1. Take the 8 over to the other side of the equation to get 3 gamma is negative 9, and then divide by 3 to conclude that gamma is negative 3. So theta is 2 and gamma is negative 3, and therefore x4 of s, reading from up here, x4 of s is equal to 2 times s plus 4 over s plus 4 squared plus 3 squared minus 3 times 3 over s plus 4 squared plus 3 squared. And then when we take the inverse Laplace transform of that, we get x4 of t is 2e to the minus 4t cosine 3t minus 3e e to the minus 4t sine 3t, all multiplied by u of t. So that's how we do that case. And now we have discussed all of the major cases that we need in order to do a number of interesting problems in the next few lectures. So that concludes lecture 19, and good luck.